We're going to talk about moments, centers of mass, and centroids. Again, this is not a BC topic, so we're going to work out on the Larson book here. So first, some vocabulary and some ideas that come from physics. Mass is the measure of a body's resistance to change in motion and is independent of the gravitational system the body is in. So we know that force is equal to mass times acceleration. So we get some weird units here. 1 pound is a weight or a force, and that's equal to a slug, which is the measure of mass in English measure, then times acceleration, which we know is going to be in feet per second squared. So on Earth, that's going to be 32 feet per second squared. So going across to the side there, find the mass in slugs of an object that weighs 1 pound. So solving for the mass, we get force divided by acceleration. So 1 pound divided by 32 feet per second is 0.03125. So that gives you this pounds over feet per second squared, and that's what I guess a slug is. Or it's also referred to sometimes as a 1 pound mass. We're not going to make a big issue of this. It's just kind of out there. But we want to understand that a weight is a force. That's something that's going to be coming up here quite regularly. So the center of mass in a one-dimensional system. So we talk about the moment about a point. And the moment is given by the mass and then times the distance from that center, from the fulcrum we're going to see. So suppose a kid with a mass of 20 kilograms sits 2 meters left of the fulcrum P, and another kid with mass 30 kilograms sits 2 meters to the right. The seesaw will want to rotate clockwise because the moment produced by the kid on the left is less than the moment produced by the kid on the right. So it's that moment there is that kind of is trying to make it rotate about the fulcrum. It's kind of a force there. So the left moment is going to be its mass times the distance. So that's going to be a 20 times 2 is 40 kilograms meters. And then the right moment is 30 times 2, which is 60 kilograms meters. So the question comes up then, how do we balance that? So to balance the seesaw, the moments must be equal. If we move the fulcrum x meters to the right, we can find out how to balance the seesaw. So we're not sure what the x is. That's what we're trying to find. So if we move the fulcrum x meters to the right, that's going to make the new left moment 20 times 2 plus x, and the new right moment 30 times 2 minus x. If we want these to be equal to each other, we can solve that and see that that's going to give us x is 2/5. So if we move that fulcrum 2/5 meter to the right, that will balance the seesaw. So that leads to this idea of what we're going to call the moment about the origin. So the measure of the tendency of the system to rotate about the origin is called the moment about the origin. We'll designate that or give the symbol m sub 0, and that's going to be the sum of the masses times their distance from the origin. So m1x1 plus m2x2 out to mn(xn). If the moment about the origin is 0, then we say the system is equilibrium. That's going to make our seesaw be perfectly balanced. For a system that is not in equilibrium, the center of mass is the point, and we're going to call it x bar, at which the fulcrum could be relocated in order to achieve that equilibrium, in order to make the seesaw be balanced. If the system were translated x bar units, each coordinate x sub I would become x sub I minus x bar, and the moment of the translated system would be 0. So that leads to, if here we're translating our distances from the origin to this unknown x bar, and we're going to try to solve that for x bar to find out how to find that center of mass. And so if we distribute that, then we get these two sums, and we want that to be 0 if the thing is going to be in equilibrium. Then if we add this summation to the other side, we get this equation. We can factor out that x bar and then divide, and that leads us to, here's how we're going to find x bar, the center of mass in a one-dimensional system. We're going to add up the moments, so it's going to be the sum of all those moments divided by the sum of the masses. Okay, let's see how that actually works in practice. So here is our example. We've got M1 is going to be a mass of 10, and it is at -5, so that means it's left of the origin. And M2 is 15, and that's right at the origin, right at the fulcrum. And M3 is 5, and it's 4 to the right. And M4 is 10, and that's 7 to the right. So the moment about the origin, we're going to add those up, is going to be M1, that's 10, times its distance from the origin, that's going to be a -5. Plus we have the 15 is our second mass, and that's going to be times 0. That's the distance from the origin, so it's right at the origin. So it's not going to, because it's right at that fulcrum, it's not going to make that thing want to rotate in either way, either clockwise or counterclockwise. Then we're going to get the third mass 5 times its distance, and the fourth mass 10 times its distance of 7. So that looks like a -50, and then 0, and 20, and 70. So I guess that's going to be 40. So that is our moment about the origin. That's our M sub 0. That's my left hand getting in the way again. And we need the sum of the masses. So that is going to be, I got to bring my pen back up now. So our sum of the masses is going to be the 10 plus the 15 plus the 5 plus the other 10. So that looks like 25, 30, 40. And so the center of mass, x bar, is going to be M sub 0 over the M. And so that's going to be 40 over 40, which is 1. So the center of mass is going to be 1 to the right. Okay, so this isn't going to be a big deal for us, but this is kind of for those physics students that may be among us there. So instead of a moment of mass, we could find a moment of force. So here that would mean the center of gravity. So we're going to look at center of mass compared to center of gravity. So since force equals mass times acceleration, then the sum of our forces, m1 times the acceleration plus m2 times the acceleration all out to mn, is going to be our total force. That's the sum of all those individual masses times acceleration. So the torque, which is, I guess, what you call a moment when you're including, when it's a moment of force about the origin, will then include these accelerations. And so I'm going to slide this to the right a little bit. So the torque about the origin is going to be the moment about the origin times the acceleration. So that would make the center of gravity, as opposed to the center of mass, the torque about the origin divided by the sum of the forces, and that's going to be our same as our moment about the origin times acceleration over the sum of the masses times the acceleration. So you can see that that acceleration appears in both the numerator and denominator and will cancel. And so we're going to see that x bar, the torque, the center of gravity, is going to be the same as the center of mass. So they have the same location. So that's not going to be a big deal for us, but that may make a difference to some physics students that may be out there. Okay, Let's go on and talk about the center of mass in a 2D system, a two-dimensional system. So now we're not just going to be on a seesaw, which was our 1D system, but now we're going to imagine that this is on this kind of plane. So you can see that it's kind of like imagining there's this like this rigid piece of maybe clear plastic or something, and we're going to set these masses down at various places on this this rigid plastic surface that has no weight itself. So instead of a single moment with respect to the origin, like we saw in our one-dimensional system, we're going to define two moments, one with respect to the x-axis, and we'll call that m sub x, the moment about the x-axis, and one with respect to the y-axis, which we'll call m sub y. So this is going to be the tendency as we place these, marbles with different masses on there. What is it going to try to make this thing rotate around the y-axis? That's our m sub y. Or is it going to try to make this thing tilt or rotate around the x-axis? And that's our m sub x, our moment about the x. So if we have these different masses, m1 out to mn, and they have their various locations given by their x and y coordinates, x1, y1 out to xn, y1, y sub n, then the moment about the y-axis, and this is maybe a little bit disconcerting at first because it doesn't seem like it's right, but if you think about it a little harder, it should hopefully make sense. The moment about the y-axis is going to be the mass times its distance from the y-axis, which is given by its x-coordinate. And so the moment about the y is going to be the sum of those masses times their x-coordinates. And likewise, the moment about the x-axis is going to be the masses times their y-coordinates. That's their distance from the x-axis. That's going to make the center of mass, which is now going to have an x and a y coordinate. We'll call it x bar, y bar, is going to be the x bar is the moment about the y, because that's got the various x distances from the y-axis over the sum of the masses, and y bar is the moment about the x-axis divided by the sum of the masses. And that m is, like we said, the sum of the masses, m1 out to mn. That's called the total mass of the system. Well, let's see how this works in practice. Let's see if we can do an example here. So if we want to find the center of mass of this system, we can see we have four different masses, and they're at four different locations. So we're going to need all these different pieces here. So the sum of the masses is going to be just adding up the 6, the 3, the 2, and the 9. And so that's going to be a total of 24, I believe. So we can then, did I do that right? 9, no, that's actually 20. Ooh, I want to make a mistake early on there. So the sum of the masses is actually going to be 20. So the moment about the y-axis is going to be that first mass 6. And remember, the distance from the y-axis is the x-coordinate. So that's going to be times 3, the x-coordinate for that first mass. Then we're going to get 3 times the x-coordinate of the second one. That's at the origin, so it's not going to contribute anything for this tendency to rotate about the x or the y-axis. Then we're going to get 2 times the negative 5, and then we'll get the 9 times the 4. So I think that's going to be 18 plus 0, and then a minus 10, and a plus 36. So let's see, negative 10 and the 18 makes 8. 8 plus 36 is 44. So that is our moment about the y-axis. We're going to need that. I'm going to come back and use that in a moment. Now the moment about the x-axis is going to be these masses times their y-coordinate. So 6 times negative 2, 3 times 0 again, 2 times 3, and 2. And so that's going to be a negative 12 plus 0. And then we'll get a 6 and an 18. So that looks like the 6 and 18 is 24. 24 minus 12 is 12. And that's going to be the moment about the x-axis. So that means x bar, the x coordinate of the center of mass, and again this seems weird, but it's going to be my over m, the moment about the y-axis, because that's giving us those things that involve the x coordinates. So that's going to be 44 over 20, and I guess 4 goes into there, 11 fifths. And the y bar is going to be the moment about the x-axis over the sum of those masses, and that's going to be 12 over 20, or 3 fifths. So our center of mass is going to be x bar, y bar, and so for us that's going to be 11 fifths, comma, 3 fifths. That's going to be like a balance point. So if you could imagine that we put those various, we had this rigid kind of rectangular piece of, say, plastic that has no weight at all, and you place these marbles of these different masses at their x and y coordinates there, then if we held a pencil underneath that plastic and put that pencil so that its tip was at 11 fifths, 3 fifths, that would make that balance. That's kind of what we're trying to say there as a center of mass. Okay, so now we work into the calculus part of things. Now we're going to imagine a center of mass of, it's called a planar lamina. And so now we're going to imagine not just these discrete masses, we're not taking these various marbles that have different weights and placing them on this imaginary rigid plastic surface with no weight. Now we're going to imagine that we have these regions, these planar regions, pieces of the plane that are going to be bounded by continuous functions, f of x and g of x, and we're going to say that this planar region here is going to have a constant density of rho. So it would be a much more complex problem if the density varied depending on where you were. But in our problem, this density is always going to be the same. It's going to be rho throughout the whole surface, throughout that whole planar region. So, and that's what we've got right here is that's rho. That's our Greek letter there to represent the density. So what we're going to do is we're going to take this this rectangle and we're going to try to kind of describe what's going to happen to this little rectangular region here, and then from that we'll imagine that we're going to divide it into n rectangles, and then of course we'll take the limit as the delta x goes to 0, and this will turn into integrals, and we'll use some calculus. So first, our mass. So if we look again at this first rectangle right here, its mass is going to be the density times the area, and the density we've said is this rho, and our area is something we've talked about before. It's going to be a base times a height, so there's our height and there's our base, and the height is going to be the top curve, f of x, minus the bottom curve, g of x, and then times the base, which is delta x. So that little delta mass right there is going to be rho times f minus g times delta x. Now the moment about the y-axis is going to be that mass times its distance x to the y-axis. So that is going to make our moment about the y-axis be that rho times our f of x minus g of x times delta x, that's our mass, and then times that value of x. That's our distance of it. So we're imagining now that we're taking the mass of this rectangle, and we're going to take all of that and put it at a single point right there in the middle of that rectangle. And so our distance to the y-axis is going to be the x-coordinate of that point right there. And that's what we're seeing in our little delta moment there. Now it gets a little more complicated on the distance to the x-axis because we're going to get our mass, which I'm going to write that. So the mass is, again, let me erase this and do it over. So our mass is going to be, again, that rho. So that's this part right here. It's going to be rho times f of x minus g of x times delta x. That's our density times area. But now what we're saying is that since we're putting this point right in the middle of our rectangle, our distance from the x-axis is going to be right there. And we're going to call that the average of the y values at f and g. So that average is going to be f of x plus g of x divided by 2. So that's going to be our distance from the x-axis. Kind of crazy. Okay, so if we can buy into that on the differential level, then we can imagine, we divide it into n rectangles. We sum those up as a Riemann sum. When we let the delta x go to 0, it's going to become an integral. So our moment about the x-axis is going to become an integral, and it's going to have that rho that we can pull out of it, and we can think of it then as we're going to go from a to b. Those are going to be our limits. We're going to have the f of x minus g of x. That's going to be the part that's coming from the mass, and that's going to multiply an f of x plus g of x. That's coming from our center, that distance, because we're going to put that mass right at the center of that rectangle, and our delta x is going to become dx, and if we want, we can pull that 2, that 1/2 from the average of the f and g out in front. So that's going to be our moment about the x-axis. Our moment about the y-axis is going to have that rho. It's going to be the integral from a to b. It's also going to have that area part of it. It's going to have that f of x minus g of x times dx, but then its distance is going to have that x, because that's going to be the distance from the y-axis out to there. And the center of mass is going to be then our moment, which is going to involve an integral, and the mass is going to be this rho times the integral from a to b of our f of x minus g of x times dx. That's going to be like the area times the density. And you can see that both of our moment and our mass are going to have that rho in it, and so that's going to end up dividing out anyway. So it isn't really going to matter since it's a constant. Okay, well, let's see if we can try to put this together here. So we're going to try to find the centroid, a region bounded by f of x equals 4 minus x squared. That's the top yellow curve, and g of x equals x plus 2. That's the bottom green curve. So we need the points of intersection, and those aren't really disguised very much. I think we can almost read them just off from the graph. You can see when x equals 1, that g of 1 is going to be 3. That's the 1 plus 2. And you can also see that f of 1 is going to be 4 minus 1 squared, which is also 3. So that's going to be a point of intersection, is that x value of 1. And we can also see that at x equals 2, negative 2 rather, both of those are going to be 0. So our interval is going to be from negative 2 to 1. So those are going to be our points of intersection or boundaries on our integral. So let's see if we can find this. So our mass is going to be rho times the integral from -2 to 1 of our top curve. That's the 4 minus x squared minus the bottom curve. So that's a minus x plus 2, and then dx. And I don't know, did I do that? Somewhere I think I did, if I can find it. I believe that's going to be a 9/2 rho. Our moment about the, let's do the easier one, the y-axis is going to be rho times our integral from -2 to 1. And the distance to the y-axis is going to be that x. And that's going to be then times our we're going to have that f of x minus g of x. Maybe I should just go ahead and write out what that is, because it's going to come up again. So f of x minus g of x is 4 minus x squared minus the x plus 2. So that's going to be 4 minus x squared minus x minus 2. So that's going to be the, see, 4 minus 2 is 2 minus x squared. So let's put that in here as 2 minus x squared. And then there's our dx. And I believe when I did that, what did I get? I think that's a -9/4 rho. -9/4 rho. And then the hardest one, I think, to find is usually the moment about the x-axis. So again, we're going to have that rho from -2 to 1. And remember, we're going to get our, this is going to be the f of x minus g of x. That's going to be the area part of it, which is going to give us our mass. And then that's going to be f of x plus g of x divided by 2. That's going to be our average value there. That's going to get the center of mass to be halfway between the f and the g, right in the middle of that rectangle. So that's going to be rho over 2 integral from -2 to 1 of, and then it gets kind of ugly. We've got the 2 minus x squared. That was our f minus g, and the f plus g, I guess, would be the 4 plus 2 would be 6. Then we'll get a plus x and a minus x squared dx. So I think when we do that, we're going to get 54/5 rho. 54/5 rho. So that is going to make our x bar. Let me bring my pen back up here. So that's going to make our x bar be the moment about the y over the mass. And the moment about the y was -9/4 rho. Our mass was 9/2 rho. So we can see that that density is really not going to matter. That's going to divide out. And so I think that's going to be a -1/2. The y bar is going to be the moment about the x over the mass. And so that was our 54/5 rho over the 9/2 rho. And again, our density divides out. And I think that's going to become, let's see, 54/5 times 2 over 9. And that will cancel. So we get actually 12/5. And so our center of mass is going to be at a -1/2, 12/5. So that is going to be the balance point in our, so you can kind of see it on the graph. So negative a half, and that would be 2 2/5 would be somewhere kind of right in there, would be the balance point. If we held our pencil underneath that rigid region there, that it would hopefully balance. Okay, one more kind of problem to look at. These are called simple plane regions. So you will be given sometimes some geometric shape here. They might have rectangles or triangles or perhaps even circles and semicircles. And we want to find the centroid of this region. So the first thing we need to do is to impose an x and y axis on here. So we might choose different x and y axes here, so you need to make that clear if this was like a test problem. So I'm going to choose this to be my axes right there. So the origin is going to be right there in the lower left-hand corner. Then what we're going to do is divide these into separate regions there. So I'm going to make these into 3 different rectangular regions. And then we're going to make it like we did that marble problem in our 2D system. We're going to find the center of mass of each of these separate rectangles, and then we're going to find the center of mass of that system. So I'm going to call this our region. That's going to be 1, and this will be 2, and that'll be 3. So the mass for that first rectangular system is going to be its area, and that's 1 times 3, so that's going to be 3. And its coordinates are going to be where that center of mass is going to be that halfway point there, so that's going to be at 1/2, and halfway there, which is going to be 3/2. So there's our first mass. And then our second mass is going to be the mass of that second rectangle. So that looks like it's 3 by 1. So it's going to also have a mass of 3. Its location, it's going to be halfway in between there. So that's going to be 1, and then another 1.5 will make that be 2.5. So I guess that's 5/2. And it's going to be a y value of 1/2. The third mass is going to be that third rectangle, and that's 2 by 2, so it has a mass of 4. And its location is going to be, we're going to be over 1, and then 2 more puts us at 3, and then another halfway over adds another 1 is going to be at 4. It's going to have an x coordinate of 4, and it's going to have a y coordinate of 1. So we're going to need our sum of the masses. So that's going to be the 3 plus 3 plus 4, and that's going to be 10. We need the moment about the x, so that's going to be the mass times its y coordinate. So that's going to be 3 times the y coordinate, which is 3/2, plus 3, and its y coordinate is going to be also 1/2, and then 4, and its y coordinate is 1. So that's going to be 9/2 plus 3/2 plus 4. So the 9/2 and 3/2 is 12/2. 12/2 is 6, plus 4 makes that 10. And our moment about the y-axis are going to be the masses times their x-coordinate. So that's going to be a 1/2 for the first one. That's going to be a 5/2 for the second one. And it's going to be a 4 for the third one. So that's going to be 3/2 plus 15/2 plus 16. And so that's going to be 18/2, which is 9. 9 plus 16 is 25. So our, did I do that right? 1/2 times 3. Oh, wait, I think I made a mistake on the x-coordinate of our mass 3. Since this was 1 and that was 3, that makes 4 plus another 1 should make this be actually 5. So let me fix that. That's going to then change this to also be a 5, which is going to make this be a 20. It's too bad. It makes the numbers worse. But that's what we actually had. So that was going to be the 18 halves is 9 plus 20 is 29. So now we can get our center of mass. The x bar is going to be the my over m, and that's going to be our 29 over 10, which is going to be 2.9. And our y bar is going to be mx over m, and that's going to be the 10 over 10, which is 1. So our center of mass will be at 2.9 comma 1. All right, very good.